Welcome to another WebGPU stream. So, last stream we ended with just a blank screen, and we spent 2 hours on that. That's okay though. Modern graphics APIs always need some patience. I changed a few things. I'll go through them soon. But basically, what we did is we I moved most of the initialization code to an application class, which now does most of this stuff. So we create a window using SDL library. We create a WebGPU instance. We create a WebGPU surface connected to this window. By the way, I moved this surface creation code to a separate kind of, not library, just a file. It is a C file, so it should work, I guess. I tested it on, on Linux, obviously. I tested it on Mac as well. It works. I didn't test it on Windows. I didn't test it on Linux with Wayland, but I guess it should work. All the code is in the GitHub repo. Its URL should be in the stream description. Yeah, so if you want to use WebGPU with SDL as well, you can just use this file. Yeah, so we create a surface, we create an adapter. I also made it so that it selects different backend types based on the system. So if it's Apple, we use Metal. If it's Windows, we use DirectX 12. Otherwise, we use Vulkan. So we create the adapter. We list its features and limits. We create the thing called a device, which is the most important thing. We'll use it to work with WebGPU. And then we select the surface format for the surface, for the window we are rendering to. And we configure the surface. This code is right here. That's basically it. Then we just do some stuff in the main loop. We'll go over that later, I guess. Yeah. So what did I change from the last from the stream? First, I moved everything to this class. Then I supported resizing the window. So if we, for example, comment out to this thing, what we'll get is this thing immediately crashes because can't get surface texture 2. What that means is when we request the next texture to render to, it is basically one of the two surface textures when we are using double buffering. This thing returns 2. So what's 2? It is this thing, it is this enum, and 2 means outdated. So we initialized the surface with one size, and then we render to it when it already has changed, when its size has changed. So this thing can't get the new surface. It says it is outdated. So in order to fix that, when the SDL tells us that the window was resized, we call application resize, which actually does this reconfiguration of the surface. Yeah, so this is the thing that we spent a lot of time on the previous stream, because with older WebGPU versions, well, not WebGPU versions, with older WebGPU native versions, this thing worked differently. You had to explicitly configure the swap chain. Triangle when? Soon. Well, I hope today. I'm just reminding you what we're doing. Yeah. I tested it on Mac, and it works if I've said about that in the building section of the repository. If you're using macOS, there dynamic library they distribute is basically broken. It has some bad dependencies that you don't have on your system. That's just seems like a bug in their packaging scripts. Yeah, so you can just remove the dynamic library and use the static library, and it will work. And if you can see, we're listing the features here. Yeah, this ones. This is just numbers, but if we go to the code that does that, this one. So we're requesting the adapter features, and yesterday I was sad that we didn't see float 32 filterable here. So basically it means that this B it translates to 11 in decimal, and there's no 11 here, so this is not supported. So if you create floating point textures, we cannot filter them. So we cannot create mipmaps, we cannot create we cannot use linear filtering and so on. And it turned out that this thing was literally implemented 5 days ago. So yeah, I guess soon we will be able to use that. Okay, so is there anything else I wanted to say? No, I don't think so. Okay, so let's make it wrangle. My plan for today is to basically go backwards. So we won't look in the tutorial, although I'll keep it open. We will try to guess what we need to do based on the API. So we know that this thing, render pass encoder, is the thing which is responsible for for rendering actually. Yeah, here we are just clearing the screen, and that's it. Oh yeah, I remembered two things that I wanted to show. First one, I added basically I'm measuring the time it takes to get the next swap chain image texture, and if we look in the logs, it usually takes about 16 milliseconds, which is pretty expected. We are rendering with 60 FPS, which is the refresh rate of my monitor. We created the surface with the first in first out mode, which corresponds to the usual vsync. So yeah, we should be having this 16 milliseconds delay. Not delay, it's sleeping, it's waiting until the next vsync. Yeah, so let's do some stuff. We want to render something, and we don't know how to do that. So this should be a method of the render pass encoder. So let's just do WebGPU render pass encoder, and then look at its methods. Oh yeah, here they are. So we can draw. Yeah, so it has, you see, it has set vertex buffer, set index buffer. We won't use index buffers yet. I don't think we will use vertex buffers for now as well. We will draw, and we will set a pipeline, I guess. The pipeline should be the thing that kind of corresponds to a single pipeline. We'll see what it does. So let's just do pass encoder set pipeline. Yep. Render pass encoder pipeline. We haven't created the pipeline yet. That's okay. WebGPU pipeline. No. What is the type of this thing? Oh, it's called render pipeline. Okay, but let's call it render pipeline. So WebGPU render pipeline. We haven't created it yet, and we need WebGPU WebGPU render pass encoder draw. So we need the render pass encoder. We have that thing. We need the vertex count. So we want a triangle. So 3. Instance count 1. We are not using instancing basically. First vertex is 0. First instance is 0. Great. So basically what we need to do is create the render pipeline. I can guess that we need a render pipeline descriptor for that. And this will create us the render pipeline GPU. I don't know, let's see. There should be a create render pipeline method. Yeah, here it is. GPU device create render. Okay, so we need the device to do that. So it's GPU device render. The device is now in the application class. So just get the device from there and we set the descriptor. And the descriptor describes what the pipeline is. Now it has a bunch of fields and let's go here. I'll just copy all of them. So the next in chain and label are null pointers as usual. We don't need them here. By the way, I think today is the day when we will actually use this thing. If I remember correctly, you need this chaining mechanism to use WGSL shaders. So pipeline layout. No, it's an object, so we need to create this one. Pipeline layout. We haven't created it yet. Let's GPU pipeline layout. The vertex state is probably not an object, it's just a struct. Oh yes, it's the struct with a bunch of stuff in it. Primitive state is a yeah. So properly filling this thing will take us a lot of time. So we are not using depth of stencils, so we can just say null pointer. Multi-sample state should be easy. Yeah. What do we have here? So multi-sample next in chain is null pointer. Multi-sample count. Let's go to the docs, shall we? What is this thing called? GPU multi-sample state. Multi-sample state. So count is the number of samples. For non-multi-sample textures, this should be 1. Bit mask. All samples can be enabled by using not alpha to coverage enabled. Well, I guess we should set count to 1. We should set mask to -1, which is all ones, and alpha to coverage enabled false. Okay, this was the easy thing. Let's go to the next easiest thing, which is the primitive state. So render pipeline descriptor dot primitive dot next in chain is null pointer, then topology. Oh, it's an enum, so I think we just need triangle list, right? What else do we have? We have strip index format. Strip index format. Since we are not using indices, we can just set whatever we want. Let's set int 32. Front face. GPU front face. Interesting. Oh, you just decide which faces are considered front faces. Well, the industry standard is counterclockwise faces. and Colin mode. Colin mode. Well, let's set it immediately to something reasonable, like back. So I hope it corresponds to the usual back face Colin, so that we don't see back faces of models. It doesn't matter right now, of course, but for future. We have set up the primitive. Now we need vertex state and fragment state. The vertex state. Place your bets. Will we be able to make a triangle in less than 1 hour? So the vertex state. Shader module, entry point, constant count, constants. So constants are, I believe, something like push constants, yeah? No, they're not push constants, they are double value. That's a weird thing. I don't know what it is, so let's just say 0 constants run vertex constant count, yeah. And the pointer to constants will be no pointer. We don't need any buffers, so buffer count 0, buffers no pointer. Okay, that's the easy part. Now we need a shader module, actually. Let's get the shaders a bit later. Let's fill in the fragment state first. So you can see that the vertex state is mandatory. You cannot not set it. It is just a field of the structure. But the fragment state is nullable, and it is specified through a pointer. That's because fragment state is optional. You can have a vertex shader without a fragment shader, which is the same like in OpenGL. You can create a shader program with just the vertex shader, and the fragment shader will do something default. It is useful, for example, when you're doing when you are doing some shadow mapping and your shader is literally just writing the depth value. Well, it's not explicitly doing this. The depth value is written implicitly. So the fragment state. Hey, what happened to the droid colony game? Oh. The time of uncomfortable questions. I kind of burnt out, I guess. It became a bit too complicated, and most of all, I was just buried in some weird game design problems, I guess. I was just adding random features and it wasn't looking like a game, and then I was adding more random features and it still didn't look like a game. Yeah. And I burned out. So the fragment state, what do we have here? Seems the stream is pausing at regular intervals. CPU, okay, drop frames. 30% dropped frames, yeah. Something is bad here. Well, I mean, it's using half of my cores to record this thing and stream it, so maybe something in the video settings is bad, but no, that's fine. That's fine. That's fine. Yeah, I don't think I can do anything else with that. Probably network problems. Okay, so let's set the fragment state. So we have the render pipeline descriptor.fragment will be the address of the fragment state. Connection not enough, perhaps. Maybe. By the way, let's not forget that we need the shader module here and the entry point. So the fragment state also has an extend chain. Let's set it to null pointer. The fragment state also has a shader module. Let's set it to unknown yet. Oops. The entry point also not done yet. Constant count 0. Constant null pointer. Target count 1 targets. So yeah, there is another thing that we need to set up, which is the WebGPU color target state. Oh Jesus, color target state. So the fragment state targets equals the address of color target state. So much explicit state. And you know, although we are doing so much explicit stuff, it's much better than in OpenGL, where you had to remember all the implicitly set state that just exists out there, and a random line at a random place that your program could mess up with the whole rendering. So right mask all, we are rendering to the whole to all channels, basically red, green, blue, and alpha. And we need the blend state. Oh, nice. Another state. Blend state. What's the blend state? Color and alpha. Oh wait, it is nullable. Okay, just set it to null pointer. I guess if you don't set it, it means that you're not using blending at all. And that's exactly what we are doing here. Okay, I think that's it. I think we are done here, except for the shaders. WebGPU shader module. So if I remember correctly, entry point is just the name of the, basically the name of the function that you will be calling from this shader module. And by the way, now that I think about it, layout. Oh, we haven't created the pipeline layout yet. Yeah. I think we can actually do all this before creating. We can create the pipeline beforehand, and then we will just set it up here for rendering and use it here. Yeah, we haven't created the pipeline layout. So how do you do that? Well, just find create pipeline layout. Yeah, it is also a function of the device. Application device pipeline layout descriptor. Pipeline layout descriptor. Another descriptor. Just when I thought I'm out, they took me back in. Next in chain null pointer, label null pointer, bind group layout counts, bind group layout. So I don't think we need bind groups yet. We will need them when we will use attributes I think, or maybe uniform variables, but we don't need them now. I hope we don't. So count is 0 and my group layouts pointer is 0. Okay, now we just need the shaders. Shaders. WebGPU, device, create, shader module. Yeah, that's exactly how we do that. Application, device. Now we will need 2 of them. So we will need the WebGPU shader module vertex. Actually, yeah, I remembered you can have a single module which has several entry points, one for each shader, so we can just have one shader module here. Shader module descriptor. So what do we have here? Yeah, that's, you see, it doesn't have anything about the source code of the shader. So what we actually need to do is use this next in chain. I'll set it to null pointer first, but then we'll do I don't know what hints are. Let's not use any hints. Now if we find WGSL, yeah, you see it, WebGPU shader module WGSL descriptor. It's a special thing that we can chain into the shader module descriptor, and we can specify the code there. Yep, so let's do that. Shader module WGSL descriptor, and the next in chain thing will be that. We can actually do it like that. Or we can cast the type here to WebGPU chain struct. This will be the same. Well, not like this, like that. Because it is the first field, we can. Yeah, it is the first field of the struct, so we can cast pointers easily. Chain next equals null pointer, and chain type equals. Let's search WGSL. Yeah, this thing. And now we can finally set the code to shader code. And let's set it somewhere. I will use C++ raw string literals for that. Yeah, let's do some shader module. Let's set up the shader module, and let's fragment main. Let's call the entry point for the fragment shader fragment main, and let's use the same shader module for the vertex shader, and it will be called vertex main. It will make sense in a few minutes. And if we run it, it says strip index format was not set to none while using non-strip topology. Oh, so if you don't use strips, so like it's not a line strip or triangle strip, you use none here. What's none? I don't know what none is. Index format. I guess it means undefined. Let's test it. Oh, yeah, unable to find entry point vertex main. This makes sense because we haven't actually created it. Okay, so I don't remember how to write WGSL, so I'll go to the tutorial. Does it? I don't think it does anything about the. Yeah, it did somewhere later. Hello triangle. Yeah, that's the thing. So we've done all that. We just need the shaders. Yeah, that's how it works. Okay, so we set vertex, then vertex main. This thing tells us that this function is, well, not us, the compiler. It tells the compiler that this function is the entry point to a vertex shader. But you can have multiple such functions in a single shader module, and then you specify, you select one of them here. Vertex main, built-in vertex index, built-in, yeah, vertex index. Yeah, so we just It's a little weird, but after GLSL and stuff, but it's fine. You can get used to it. Yeah, so we just write a function. We declare that it is the entry point to a vertex shader. We say that we want this argument of the function to be the built-in vertex index, which will be from 0 to 2. And we say that the return value of this function is the position of the vertex. And all we do here is if in vertex index is equal to 0, return like for f. So we want a triangle. Let's do minus 0.5. Oh, you don't need f here. I don't know, let's do minus 0.5, minus 0.5, 0, 1. Else, if it is the first vertex, we return another hard-coded thing like this. Or it is the second vertex, we return something else, like maybe this. Otherwise, we return something just like that. Okay, and the fragment shader, let's just copy that. Yeah, so this function, this says that this function just returns the color for the 0th color attachment, and if you remember, we have yeah, this color target here. Fragment. Where do we say that we are rendering to the? Oh yeah, in the render path descriptor. That's where we say. That's where we describe the color attachments. Okay. I'm not exactly sure what this 0 refers to, but that's fine. Unbelievable. We have a triangle. 48 minutes into the stream. So the stream started something like 15 minutes before we actually started doing it. So it's something like 30 minutes. 30 minutes to get a triangle. Not bad. Yay. I think this deserves its own commit. Ooh. Yeah. I'll refactor it later. Okay, let's make it let's make the vertex shader also return the color so that it has like a nice gradient. I don't remember how to do that, but I think if we Google WGSL, we will get to the documentation. Oh, it has an example. Great. So I think you just declare a struct here, like vertex out, and we will have a position here and the color. Let's see if this compiles. Yes, it does. Okay, so now we just return the vertex out thing. The position is like that, and let's make this thing red. Let's make this thing green. And let's make this thing blue. And otherwise just black. I think this should work. And so something is wrong. Entry point vertex main at vertex is invalid. Struct member 1 is missing a binding. I have no idea what that means. Let's maybe go to the tutorial and see. Some shader examples. Yeah, so you can say vertex input, vertex output. Oh yeah, so you need to specify the allocations for them. Okay, and you also need to, yeah, let's go to output. So you need to allocation 0. Vertex output, output. Another error. And in here we can probably accept the vertex output. I don't know. No, we probably can't. Yeah, we can. We actually can. Okay, so let's call it vertex, and then we'll just return vertex color. No? Oh yeah, this is not the syntax of this language. Yay! We have a colored triangle. 14 minutes into the stream. Not bad. I can even resize it. Hehe. Okay. Let's do color correction on it. Oh snap, it's a triangle. Yeah. Here it is with gamma correction. Okay. colored triangle. So what do we do now? I think the logical next step is to have some buffers with data. By the way, do I need this semicolon? No, I don't. Nice to know. Okay, so we need to set up vertex attributes, and this is something I don't want to guess. I think I will follow the tutorial with that. Yeah, the hollow triangle uses hard-coded vertex positions as we did. So let's go to the input geometry. Yep, so we need to create a buffer. We need to write some data to it. We need to yeah, we don't need to map them. First vertex attribute, yeah, that's what we need. So we create the buffer, we load the data, and we create a vertex attribute. There's a limits, setting up the buffer, loading the data. Yeah, so you need to set up vertex buffer layout. Okay, I guess we can try. Let's make a struct vertex input, and it will be, what's up with this indentation, location 0, position back 4F. And maybe let's also store the index here as well. And then we can do vertex input here in vertex input. And then we have in.index here. Yeah, let's call this thing in as well. I think it should compile, but it will fail to link or something like that. Location 0, interpolated as some perspective, is not provided by the earliest shader stage in the pipeline. I think it refers to this thing. Yeah, we didn't set up this attribute. Is this how they did this in the tutorial? I think they, yeah, I think that's it. So we will use just two floats for the position, and we will do in.position here. Well, actually, let's have two attributes. No, let's not. Let's have one attribute first. Let's just return. Let's make a red triangle first. We will sacrifice the colors. Now we need to specify this thing. So, where do we do this? Probably in the vertex state, yeah? I'm not sure. Yeah, so we create a buffer object, we write data to it, that's easy. Now we create a, we need to specify a buffer layout here. So we will have one buffer, we will have GPU buffer layout. What is this? Oh, what is this thing? Vertex buffer layout. Okay. Vertex buffer layout. So it goes here. So erased right. Interesting. Let's say 0. I hope this will work. Step mode equals vertex step mode vertex. I guess this is for instance rendering. So if this buffer was for instance attributes, we would set instance. Vertex buffer not used. No idea what's that. Attribute count is 1, and then we need to set up the attributes. GPU vertex attributes. Let's make it an array because we will have more attributes here. So we need to say the format, the offset, and the shader location. That's easy. So format equals oh, nice, float 32 times 2. I guess that's 2 floats. Now the offset is 0 and the shader location is 0. Great. Now we have the layout. We also need to actually create the buffer and set it in the, I guess here we set the pipeline. We will need to set the vertex buffer. Plus encoder slot buffer offset size. Oh, so I think slot is this thing. So this can be an array. We can have several buffer layouts, and each layout corresponds to a single buffer. I hope. That's my understanding. The buffer is, well, we haven't created it yet, but we'll do that in a minute. Offset 0, size. Oh, we need to know the length of the buffer when we set it. We haven't created this yet, but we will do that in a minute. So we have the render pipeline. Let's create vertex. We will have just the position. Let's have a vector of these vertices. Let's just initialize them right here. We'll have a vertex at minus 0.5, minus 0.5. Let's do it like that. Here and here. Okay. Now we need to create a buffer with GPU buffer descriptor buffer descriptor. Let's call it vertex buffer descriptor. We have the next in chain pointer, we have the label pointer. we have the size, usage, and method creation. Let's specify them in the order of their declaration. So usage. What's usage? Yeah, it is a bit mask. So we will copy to this thing. So we will write data from the CPU to the GPU buffer. So it is a copy destination, and we will use it as a vertex buffer. So I think we need to say this or this. Size, vertices size times size of vertices 0, and method creation false. We don't need to map it. Now let's create the buffer. Application device descriptor, it's here. Then I think you need to do something like WebGPU queue write buffer. Yeah, queue is application queue. Buffer is vertex buffer. Buffer offset is 0. Data is vertices. Data size is the same. Vertices size times size of vertices. And I think this should work. Yeah. Of course it doesn't. Though I don't know why. It doesn't complain that we have a bad attribute. We now have a vertex attribute which we are setting correctly. I hope we do. I'm not sure about this erased right thing. Let's go to the documentation. There should be a vertex buffer layout thing. Vertex buffer layout. Yeah. The stride in bytes between elements of this buffer. Oh, you probably cannot say 0. You need to say something like 8, which is, well, actually size of vertex. We haven't declared it yet, so let's move this class a bit. Maybe here, or maybe even besides the shader. Yay, it works. Okay. So in OpenGL you can say that the stride is 0. Where is it? This thing. You can say that the stride is 0, and it will mean that the attributes go packed tightly in the buffer. So you could say 0 instead of actual size in bytes, and you cannot do this with WebGPU. Okay. Now let's add a color. No, let's commit this thing. Now let's add colors. I will store it as just an uint32. And I need to declare it here. It will be the first attribute. It will be color. It will be a 4-dimensional vector, and we will just return it here instead of a fixed color in .color. Yeah, I quite like this shader language. It is a bit weird, but also so clean with all this location attributes and custom structs. Yeah, we need let's initialize the vertices still. So it will be in RGBA, so I want this thing to be red, I guess. Let's U. This one will be green. This one will be blue. And now we need to set up the attribute. It should be as easy as just setting up this thing here. So we say that we have two attributes. The format is u int 8 times 4. Offset is 8 bytes. Shader location is 1. Nope. Oh, you probably need to say that it is normalized. Yeah. It is a unorm 8x. Yeah, so uint is for integer attributes. If we said like u32 here, but we set a floating vector, so we need it to be a floating point normalized format. Makes sense. Yay! Well, okay, we are almost ready to do some real graphics programming, I guess. We're about 1 hour into the stream. Let's work on the camera, shall we? So, yeah, first let's figure out how to set up uniform variables here, and then we will use some actual matrices. Does the stream still lag? I see that it does. Oh, it's dropping half of the frames. That's not a good thing. So yeah, uniforms, shader uniforms, the first uniform. Yeah, so we need to that's quite a mouthful, but we'll manage. So we need to specify let's say it view projection. How do you do matrix types in VGSL? Transpose matrix. Yeah, that's how. Mod 4x for f, a 4x4 floating point matrix. So we are specifying that it's a uniform variable. This thing is the address space. It can be something like workgroup local for compute shaders and stuff like that. Then we say that it is in the 0th group and has a binding of 0. So you can have multiple groups that attach some resources to your shaders. And this thing is the 0th in the 0th group, something like that. What we'll do here is just multiply this thing by the pre-projection matrix. That should do it. It will say that we haven't specified this binding group. Shader global resource binding is not available. Yeah, so we haven't actually specified this thing here, and the way we do it is in the pipeline. There should be something called binding here. Oh yeah, here it is, in the pipeline layout descriptor. Bind group layout counts, so we need 1. What's the type of this thing? Yep. Wait. Yeah, I copied the wrong thing. We need the bind group layout descriptor. Bind group layout descriptor. So I don't remember how you do that. I'm just following what the API tells me. Yeah, so it has an entry count and an entries array, which is an array of these things. Okay. Bind group layout entry. Teenage Mutant Ninja Turtles. Oh, it has a lot of stuff in it. Okay, let's just copy all that. Next in chain is null pointer. It doesn't have a label. Okay. Binding is okay, so we have bind group layouts. This array will correspond to this 0 group, and then in each such layout we can have multiple entries, and each entry has a binding, and this binding is what this thing is. Okay, makes sense. Binding 0. Visibility. This thing should be visible to the vertex shader. Is it a bit mask by the way? Yeah, it is. Now this thing has several things here. If I understand this correctly, you can have either a buffer or a sampler or a texture or a storage texture in a single layout entry. So you need to kind of set the other things to 0. Yeah. Okay, what do we need to specify for the buffer? Next in chain null pointer. Type is uniform. This tells the thing that we will use this buffer for uniform variables. Has dynamic offset. No, I don't remember what that is. It doesn't matter. Buffer max binding mean binding size. There should be something about this. What this thing is called. Buffer binding layout. bind group entry. Buffer binding. Maybe it's not a bind group entry, maybe it's a bind group layout entry, yeah. Oh, Jesus. Yeah, so if it's a buffer, it has a min binding size. Mention this entry. It isn't optional though in the Rust API, but I don't think it can be optional here. Okay, whatever. We know that this is a 4x4 floating point matrix, so it's 16 times 4, oh, 64 bytes. Okay, that's for the buffer. Now, this binding doesn't have any samples, so I guess we just say that the sampler type is undefined. Sampler buffer, is this all we have to say about the sampler? I guess. Texture. I'm not sure that I'm doing this right. Let's see. Yeah, so they are setting that the buffer is like that. Yeah, I guess we just initialize everything else to default values. Sample type undefined. This is basically a way to do variants or sum types in C. View dimension is undefined. Will do. And we have a storage texture, and we also need to set everything to null here. Oh, whatever default values it have. Access undefined. Format. I guess undefined. Yay. And what else does it have? It has a view dimension, also undefined. Phew. This is how we send one matrix as a uniform variable. Okay, no, this is not how we send it. This is how we describe this matrix, essentially. Now we need to actually send it. Let's just compile this thing and see what happens. Oh, I think it just crashed. Yeah, it just crashed. Well, yeah, we said that we have one matrix. We have 64 bytes from some buffer, but we didn't attach this buffer here. How do you do that? I think there should be something like set bind group. Yay. So set the group index 0, bind group. We will create it soon. The group, the dynamic offset count is 0. The dynamic offsets is null pointer. I don't remember what dynamic offset is. GPU bind group. Well, actually, I think we can create it before as well. I hope we can. Bind group equals WebGPU device create bind group. Yeah, yay. Bind group descriptor. So we had a bind group layout descriptor. Now we actually create the bind group itself. What do we have here? Next in chain null pointer, label null pointer. It would be a good idea to set this labels to something reasonable, but I think we'll spend half of the stream just figuring out the names. Yeah, here we just reference the bind group layout we created earlier. Didn't we have a bind group layout? Wait, we have a bind group layout descriptor. Oh, yeah. That's why it crashed. We said that we have one bind group layout, but we set the array of bind group layouts to a null pointer. We didn't actually create it. Oh Jesus, device create bind group layout. Yep. Application device bind group layout descriptor. Yeah, now we should have it. Now we should have the bind group layout. Okay, and we can reference it here. Entry count probably 1. I don't know what entries are, but we'll figure it out soon. Bind group layout entry. What's a layout entry? Oh Jesus, it's the same thing. Well, not literally the same thing, but it is a similar thing. Next in chain is null pointer. What? Why? Why do you think it is it is not a layout entry, it is a bind group entry. Yeah, that's the problem. Okay, I see. So it's a bind group entry. And now, yeah, it has slightly different fields here. Or maybe not. I don't know. Not the layout entry, but the group entry. So binding 0, buffer uniform form buffer. We'll create it soon. Offset 0, size 32 bytes, no, 64 bytes, yeah. Sampler is null pointer, and the texture view is null pointer. Okay, this was easy. Now we just need to create the uniform buffer. For now, let's just have a fixed matrix. View projection matrix, 16 floats. I don't know if they're column major or row major. Well, it doesn't matter for the identity matrix, of course, but we need to figure it out. So we need to do basically the same thing, but with the uniform buffer. Uniform buffer descriptor. We need to change the usage to uniform. We are not going to store vertices here, we're going to store uniforms here. Its size will be 64 bytes. Yeah. We have created the uniform buffer, then we need to write data into it. From here, 64 bytes. Okay. Is that it? I mean, it compiles and it runs. I guess we have successfully passed a single 4x4 matrix to the shader. Congratulations. 1 hour 15 minutes into the stream. Nice. Okay. Yeah, the connection is really bad. Is anybody still watching this? Is it bearable? Do you understand at least half of what I'm talking about? I mean, do you hear at least half of what I'm talking? So let's scale it twice in the x direction. It works. Now if I say 0.5 here, I have no idea what happens. Yeah, so it is column major. So if I wanted to offset my triangle by 0.5 in the x direction, I should write it here. It is column major. Okay. Can we say that this column major I mean, yeah, they're just column major, you can't change them to anything else, I guess. Okay, whatever. Let's maybe do something like change this matrix later in the loop, and I don't know. Let's use frame ID as our time indicator. So let's create the matrix which has, I don't know, which rotates. I think we need it like this. for a counterclockwise direction. Yep, it works. It is distorted, of course, because we have because the aspect ratio of our screen is not equal to 1. Basically, it's not a square. If I make it square, it kind of rotates nicely. Kind of. I think I want to measure actual time here, so let's do like yeah, that's how you compute the time in C++. Okay, now it should be working with real time instead of the frame ID. Let's end it as well. Dynamic uniform matrix. Yeah, now I think I want to add the GLM library and create an actual matrix. Is this how you do it? Yeah, I guess you just include this thing. Why is it so slow? Let's no, we don't need to add subdirectory. GLM is header only, so we can just add its include directory here, and that's it. Yep. Run cmake. Yeah, so if we put GLM, yep, GLM, I think that should do it. Now instead of having this projection matrix, let's do GLM mat4 U matrix GLM rotate. No, where do you do? How do you rotate it? Oh, it's in the GTX transform transform to GSGLM. This is such a fucked up library. Rotate, angle, and vertex, vector, and yeah, okay, so rotate by time angles around the vector 0, 0, 1, yes. And the projection matrix will be just an identity matrix. And then we'll have the view projection matrix, which is the product. And then we just take its address here. This should work. Yep, it does work. That's pretty boring though. Let's do something else. Let's triangle. Yeah, we did a triangle. It took just about 30 minutes, I think. Now I trying to rotate it. It took another hour. Yeah, let's set up a GLM projection. No, it's called perspective. Yeah, let's do a perspective projection. So for Y, field of view in the Y direction. I don't know, maybe 45 degrees. Does it expect degrees though? I don't know. I hope it works in radians. Aspect ratio, so that's the width of our display divided by its height. Z near, I don't know, something small, something large. Now the view matrix, I mean, I guess if you just set it to an identity matrix, we won't see anything, will we? Yeah. Why? Because we're looking at the negative Z direction. Yeah, let's do a translation. So we are looking into the negative Z direction, so we want to translate our scene into that direction. So 0, 0, minus 5, maybe? I don't know. Yep, there it is. Let's do some fun stuff now. Let's set up the camera. We will have a camera position. Let's start with here. We will have a camera X angle and camera Y angle. We won't change these angles just yet. No, we will do that. So we won't change the projection matrix, but the view matrix will translate the scene like that. Like in what order do we need these things? We rotate the scene. Then translate it. No? No, I think we first translate and rotate. Yeah. GLM rotates. So camera X angle. X is like a horizontal angle, so we will rotate around the upward direction, which is Y, and we will rotate by the Y angle. Maybe we need to do this in a different order. We'll figure it out soon. So let's do another thing. Let's do, yeah, so for now it will just do the same as before. Yeah, now we need to set up some stuff with the mouse. I think we do SDL set relative mouse mode true. Yeah. What's wrong with you? Oh Jesus, okay, SDL true. Now when I run it, I won't see my mouse because it is, yeah. And we need to react to mouse events. Case SDL mouse motion. Here it is. Let's create float camera sensitivity, sensitivity, yeah. Something like that usually works. So camera X angle, we add event motion X relative times camera sensitivity. The same for the Y angle, Y relative, break. We should be able to rotate the camera with the mouse now. Oh Jesus, no, this was too high. Nice. Maybe this is a bit too fast. Let's do it like that. Great. Also, let's no. Let's do some. Yeah, are the angles in the proper order? I don't know. I'm not sure. I think they are. Okay, now you know what, let's do something like that. So let's make an unordered map with the currently pressed keys. No, not a map, a set. Set STL I don't remember exactly what do we need here. Keys down. Yeah, I think we need the scan code. Yeah. And if still key down, yep, we insert the pressed key here. Event key, sim scan code. And if it is key up, we erase this thing from the set. Okay, now if keys down contains SDL scan code, let's say A, no, let's say W to move forward. I think we need to compute the camera forward vector for that. How do we do that? Wait, why? I thought this thing should be minus angles. Well, whatever, it works. Okay, let's handle the X angle first. So We will, so by default we look in the 0, 0, -1 direction, but then we rotate around the y-axis, so we should have something like cosine camera x angle here and sine camera x angle here. Let's also create a camera speed. So if the W key is pressed, we say camera position plus equals camera forward. This times the camera speed times the time delta. What happens now? Yep, I am moving forward. Looks a bit weird, but that's okay. Yeah, if the S is pressed, we do the same but backwards. Let's increase the camera speed to something like 3. No, the angles are wrong. They need to be in a different order. Like that. Yeah, now it feels better. Okay. Now we need to figure out how to go upwards and downwards. So the y angle of 0 means that we are, yeah, so I think we need to plug in sine here and cosine here. These are basically spherical coordinates, which I am just guessing right now. Usually works. Probably need to stick minus somewhere. Well, maybe here. Yay, it works. It works. Great. Well, that's quite something. Camera sideways. Let's also support moving to the right or to the left. So this doesn't depend on the camera Y angle, just the X angle, and we need to kind of rotate it 90 degrees. I don't know in which direction, so I'll just insert some signs as I feel like. I don't know, maybe like that. Yeah, this vector should be orthogonal to this one if camera Y is 0, so we will get, yeah, so we shouldn't have minuses here, or we should have minus in both of these things. So A will be, camera sideways is a bad name, let's say camera right. Yes, so it's to the right. Oh, it's easy to guess. It should be 1 if the X angle is 0, and it will be 1. Yeah, okay, this should be right. If we press D, we go to the right. If we press A, we go to the left. Yeah, it works. I can now move around. Oh, see, we don't see this triangle from the inside because we have set backface calling to true. Great. Well, we have some more time left. Let's do something like something silly, like I don't know. Let's make an icosahedron. Yeah, just let me copy the vertices. Yeah, that's great. Oh yeah, indices. We didn't do index rendering. I think that's what we should do first. Okay. No, let's not. Let's not do that. Let's just copy the icosahedron here. So, yeah, I'll just slap it here. I'll comment out these things and our vertex, so it has a color. Yeah, that will do. So what we'll do here is for let's uncomment this, so these are not used. These are defined. Let's do let's not do them like that. Let's do something like yeah, something like that. Let's format this code properly, well, somewhat properly. I will hide this under a scope. Now, for each icosahedron triangle, what we'll do is we add vertices. We need some way of figuring out a color. Okay, let's have some fun. Let's keep it like that, and then we will have default uniform int distribution int 8 maybe even 32. Random color, like that. And let's select the color, random color from the RNG, and then we just create 3 vertices. Vertices pushback, icosahedron vertices. So its position is icosahedron vertices triangle 0. Its color is color. What's wrong? Oh yeah, it's not a. Yep, we need to fix that. We don't have X and Y here. Let's have a like 3 position, and we need to update some stuff here. In order for this to work, we need 3-dimensional position, so we don't need this. We don't need where are the attributes? They're here, so type is float x3, and the offset to this thing is now 12. Attribute count 2. Yeah, everything should be all right now. And let's just replace this thing with GLM 3, like that. Yep, this should work. Now we do this. We have a triangle list, and here we have vertices.size. Instead of just 3 vertices, we have this many vertices. Let's see. No, oh yeah, we don't have a depth buffer, so they are just rendered. Wait, are they in an? Yeah. So because this thing is convex, we don't need the depth buffer. We can rely on backface culling, but obviously this thing is not culling the proper faces. That's because I guess these vertices are in the wrong order, so we just swap the vertices and it should work. Yeah, now it looks like an icosahedron. Let's remove gamma correction. I don't think it looks nice with random colors. I want it to be more random, more pronounced. Yeah, like that. Well, that's something. Let's do normals. Normals. Yeah, why not? Let's do normals, hacker ham. Vertex input, I'll leave the colors, though I will make it a single color so that we can see the normals. Now the normal itself will be a 3-dimensional vector, I guess. We can, oh no, it's not STD, it's GLM. We can compress them, but I don't think we need to do it now. So yeah, we have the normal. Now we will need to output this normal into the fragment shader, and then we have let's just do something like in color multiplied by 0.2 plus 0.2 times the dot product of normalized normal, and some random light direction, like, I don't know, it's 1, 2, 3, usually works. Now it will crash because we haven't defined this attribute. Yeah, and it means that we have written a proper shader. This is okay with the code is okay. We just need to set up the attribute. Let's set it up. We need 3 attributes here, obviously now. The last one is also float 32 times 3. 2, 2, 2. The offset is 16 bytes, I believe. Shader location is 2. Okay. Now let's set the colors to white. No. I want some nice color. Let it be blue. And we need normals, so let's do something like that. 3, like that, like that, like that. 2, 1. Vertex is 0. Vertex is 1. Vertex is 2. Cross it. Yeah. That's exactly what I'm going to do. So we take 1 minus 0 and 2 minus 0. I think that's how we do it. And we set this thing here. No. Oh, that's I'll rename it to something even more verbose. That's okay. I thought I set it to blue. Oh yeah, that's not how it works. Now you can barely see it. And this thing is also completely black. Oh, that's because I forgot to normalize the actual light direction. Yeah. Yep. That's it. We have a lit icosahedron. I don't like this color. Let's just make it white. No, that's just boring. Let's make it magenta. Okay, let's just commit it. Let's remove the randomness for now. The last thing I want to do today is to make the camera a little bit more smooth. So I'll use my favorite trick for that. Instead of updating the actual camera angles, we will update some helper variables, and then in the loop we will do something like that. I don't know, 20 maybe. So just nudge the actual camera angles towards this target values over time. Yeah, now it moves extremely smoothly. It feels nice. Boop. No icosahedron inside. Yeah, I guess the next logical step would be to set up a depth buffer for this thing. Well, I guess that's it for today. 4 people left on the stream. Yeah, as I've said, the code is in the GitHub repository, so it should work, it should be fine. Thank you all for watching.